27-year-old Princeton graduate student, overweight, chain-smoking, drinking heavily, typed 137 pages in 1956 that rewrote the foundations of physics. His advisor carried the manuscript to Copenhagen, to the court of Niels Bohr. A seminar was arranged. One physicist dismissed the work as theology. The manuscript was shelved. The student left physics forever, spent his career calculating nuclear war scenarios at the Pentagon, and died at 51 of a heart attack, alone in his bed. Per his instructions, his ashes were placed in the garbage. His name was Hugh Everett III. His theory is called the many worlds interpretation, and 68 years after it was dismissed, it remains the most radical answer ever proposed to the deepest question in physics. What happens when you make a measurement? By the end of this video, you will understand the measurement problem that has haunted quantum mechanics since 1927. You will examine Everett's solution and the price it demands. You will see why the leading interpretations all fail, and you will follow the evidence to its rational conclusion. If you find value in explorations like this, in understanding the deep puzzles that keep physicists awake at night, consider subscribing to the channel, which helps these deep dives reach more curious minds. Now, let us begin. The measurement problem is the oldest unsolved question in quantum mechanics, and it is the reason Hugh Everett's many worlds interpretation exists. To understand the problem, we must first understand the man, the equation, and the contradiction that drove one to solve the other. Hugh Everett III was born on November 11th, 1930, in Washington, D.C. He was, by all accounts, brilliant and eccentric, a mathematics prodigy who wrote to Albert Einstein at the age of 12 and received a reply. He entered Princeton University for graduate study in physics in the early 1950s, where his advisor was John Archibald Wheeler, born 1911, died 2008, American physicist, the man who coined the terms black hole, wormhole, and it from bit. Wheeler was one of the most creative minds in 20th century physics, a collaborator of Bohr and Einstein, a mentor who encouraged radical thinking. Everett was the right student for the right advisor. The story of how the many worlds interpretation was born involves, according to multiple accounts, an evening in the autumn of 1954. Everett, his friend Charles Meisner, and Arj Peterson, Bohr's assistant, were drinking sherry at Princeton and discussing the foundations of quantum mechanics. The conversation turned to the measurement problem, the problem we are about to examine, and Everett began to develop the idea that would become his thesis. He worked on it through 1955 and delivered a long draft to Wheeler in January 1956, approximately 137 typed pages, originally titled Wave Mechanics Without Probability, later retitled The Theory of the Universal Wave Function. Wheeler was intrigued but cautious. He carried the manuscript to Copenhagen in the spring of 1956, hoping Bohr would engage with it. The seminar was held. The reception was hostile. Alexander Stern called it theology. Bohr did not engage with the argument. Wheeler, caught between his loyalty to Everett and his reverence for Bohr, asked Everett to cut the thesis roughly in half. The filed dissertation on the foundations of quantum mechanics, defended on April 23, 1957, was a compressed version of the original. The short published paper Relative State, Formulation of Quantum Mechanics appeared in Reviews of Modern Physics in July 1957, accompanied by Wheeler's cautious companion assessment. The theory was published. The physics community ignored it. In March 1959, Everett and his wife Nancy travelled to Copenhagen for approximately 6 weeks of meetings with Bohr and Peterson. They stayed at the Hotel Österport. The meetings went nowhere. Bohr refused to engage with the central argument. Everett later described the trip as doomed from the beginning. He returned to the United States, joined the Weapons Systems Evaluation Group at the Pentagon, and never published another physics paper. He co-authored classified documents on nuclear strategy, including WSEG-50, a key document in the development of mutually assured destruction. He co-founded Lambda Corporation in 1964, a defense consulting firm. He drank heavily. He smoked 3 packs of cigarettes per day. He became obese. He died of a heart attack on July 19, 1982, at the age of 51, in his home in McLean, Virginia. His son Mark, then 18 years old, later the lead singer of the rock band Eels, found the body. Everett had left instructions that his ashes be placed in the garbage. They were. The family tragedy did not end there. Everett's daughter Elizabeth, known as Liz, had attempted suicide roughly a month before her father's death. When told, Everett reportedly looked up from his newspaper, said, "I didn't know she was that sad," and returned to reading. Liz died by suicide in 1996, an overdose. Her suicide note requested that her ashes be thrown out, so she might end up in the correct parallel universe to meet up with Daddy. Nancy Everett, Hugh's wife, died in 1998 of lung cancer on what would have been Hugh's 68th birthday. The family that invented the multiverse was destroyed in this one. Now let us examine the equation that started everything. The Schrödinger equation, IH bar partial psi by partial t equals H hat psi. This is the fundamental law of quantum mechanics, written by Erwin Schrödinger in 1926. I is the imaginary unit. H bar is the reduced Planck constant, approximately 1.055 times 10 to the negative 34 joule-seconds. Psi is the wave function, the mathematical object that encodes the complete quantum state of any system. H hat is the Hamiltonian, the operator encoding the system's total energy. The equation is deterministic. Given psi at any moment, the equation specifies psi at every future moment with mathematical certainty. The equation is linear. If psi A and psi B are both valid solutions, then any combination of psi A and psi B is also a valid solution. This property, linearity, is called superposition. It means a quantum system can exist in multiple states simultaneously, with each state contributing an amplitude to the total wave function. The equation is beautiful. It is precise. It has been confirmed by every experiment in the history of quantum mechanics, from the double-slit interference pattern first demonstrated by Thomas Young in 1801, through the single electron buildup filmed by Akira Tonomura in 1989 at Hitachi, to the interference of massive oligoporphyrin molecules weighing more than 25,000 atomic mass units, demonstrated by Marcus Arndt's group in Vienna in 2019. The Schrödinger equation works. It has never failed. The problem is what it predicts. The equation predicts that a particle passing through a double slit exists in a superposition of passing through both slits simultaneously. The equation predicts that an atom in a magnetic field, as in the Stern-Gerlach experiment performed by Otto Stern and Walter Gerlach in Frankfurt in 1922, exists in a superposition of spin-up and spin-down. The equation predicts that a measuring device interacting with a quantum system enters a superposition of showing every possible result simultaneously. The equation predicts that you, the observer, upon looking at the measuring device, enter a superposition of seeing every possible result simultaneously. The equation predicts that the universe, at this moment, exists in a vast superposition of every possible configuration of every particle. We never observe this. We observe one result, one spin, up or down, one reading on the detector. This value, not that. One world. Definite, singular, classical. Schrödinger himself saw the absurdity of his own equation's predictions. In 1935, he proposed the most famous thought experiment in the history of physics, Schrödinger's cat. A cat is placed in a sealed box with a radioactive atom, a Geiger counter, and a vial of poison. If the atom decays, a quantum event with, say, a 50% probability in 1 hour, the counter triggers, the vial breaks, and the cat dies. If the atom does not decay, the cat lives. According to the Schrödinger equation, after 1 hour, the atom is in a superposition of decayed and not decayed. The Geiger counter is in a superposition of triggered and not triggered. The vial is in a superposition of broken and intact. The cat is in a superposition of alive and dead. Both states exist simultaneously in the wave function. The equation does not select one. The equation predicts both. We open the box. We find one cat, alive or dead. Not both. Not a blurred superposition. One definite outcome. What selected it? The equation did not. The experiment did not. Something happened between the quantum superposition and the definite observation, and the Schrödinger equation does not describe what. The strangeness deepens when we examine experiments that probe the boundary between quantum and classical. The Wheeler delayed choice experiment, first proposed by John Archibald Wheeler in the 1970s and confirmed experimentally by Vincent Jacques and colleagues in 2007, demonstrates that a measurement choice made after a photon has entered an interferometer can retroactively determine whether the photon behaved as a wave or a particle. The photon does not decide what to be until the measurement is completed. The past, in some sense, is not fixed until it is observed. Jacques's team used a quantum random number generator to insert or remove a beam splitter at the interferometer's exit, with the random choice space-like separated from the photon's entry. The results: 94% visibility with the beam splitter, wave behavior, less than 1% without it, particle behavior. The measurement setting, chosen after the photon entered the apparatus, determined the photon's apparent history. In 2000, Yun-Ho Kim and colleagues performed the delayed choice quantum eraser experiment, demonstrating that interference can reappear after detection if the which path information is erased. Two entangled photons are produced. One, the signal, goes to a detector screen. The other, the idler, goes through a setup where its path information can be preserved or erased. When path information is preserved, no interference pattern appears in the signal photons. When path information is erased, even after the signal photon has been detected, interference reappears. The pattern depends not on what happened to the signal photon, but on what happened to its entangled partner. The quantum correlations do not transmit signals. No faster-than-light communication is possible, but they demonstrate that the reality of a quantum event is not fixed at the moment of detection. It depends on the entire experimental context, including measurements that have not yet been performed. What does it mean that the behavior of a photon, whether it acts as a wave or a particle, depends on a measurement choice that is made after the photon has already passed through the apparatus? These experiments are not speculative. They are not thought experiments. They are laboratory results published in peer-reviewed journals, reproduced by multiple groups, confirmed to high statistical significance. They tell us that the quantum world does not operate the way classical intuition demands. Superposition is real. Entanglement is real. The measurement problem is real. And no interpretation of quantum mechanics, not Copenhagen, not many worlds, not Bohmian, not GRW, has resolved the tension between what the equations predict and what we observe. This is the measurement problem. The equation predicts superpositions. We observe single outcomes. Something selects one result from the superposition. The equation does not say what. The equation does not say when. The equation does not say how. The most fundamental law in quantum mechanics, the most confirmed equation in the history of physics, does not describe the most basic feature of our experience, that we see one thing at a time. Think about this through an analogy. Picture a novelist who writes a story in which every chapter ends with the protagonist facing two doors. The novelist writes both possibilities, door A and door B, in parallel, weaving both storylines forward simultaneously. But when you read the novel, you experience only one door per chapter. Something selects which storyline you follow. The novelist's manuscript does not contain the selection rule. The manuscript contains both storylines, equally real, equally developed, equally detailed. The selection happens when the book is read, but nothing in the manuscript explains the selection. The Schrödinger equation is the manuscript. The measurement problem is the missing selection rule. What does it mean that the most fundamental equation in physics, an equation confirmed to 12 decimal places, does not contain a mechanism for producing the definite outcomes we observe in every experiment? The Copenhagen interpretation, developed by Niels Bohr, born 1885, died 1962, Danish physicist, Nobel Prize, 1922, and Werner Heisenberg, in the late 1920s, resolved the measurement problem by postulate. Copenhagen declares that upon measurement, the wave function collapses instantaneously, non-deterministically, irreversibly, into one of the possible outcomes. The probability of each outcome is given by the Born rule. P of x equals the absolute value of psi of x squared. This is the second equation that matters for our story. P of x is the probability of finding the system in state x. Psi of x is the wave function's amplitude at x. The probability is the square of the amplitude. Max Born proposed this rule in 1926 and received the Nobel Prize for it in 1954. Copenhagen works. It gives correct predictions for every experiment. It is the interpretation taught in every textbook, used in every laboratory, applied in every calculation. And it contains a contradiction so fundamental that it has troubled the deepest thinkers in physics for nearly a century. The contradiction: the Schrödinger equation is deterministic. The Born rule is probabilistic. The Schrödinger equation preserves superpositions. The collapse postulate destroys them. The Schrödinger equation is reversible. Collapse is irreversible. Copenhagen asserts both deterministic development between measurements, random collapse during measurements, without specifying where the boundary between and during lies. This is the Heisenberg cut, the line between the quantum and the classical, between the system and the observer, and Copenhagen draws it arbitrarily, with no physical justification. Is the cut at the particle, at the detector, at the observer's retina, at the observer's brain? Copenhagen does not say. It cannot say. Think of this through an analogy. Picture a courtroom where two laws govern proceedings. Law 1 says all evidence must be preserved. Nothing may be destroyed or discarded. Law 2 says the judge, at the moment of deliberation, must destroy all evidence except one piece and base the verdict on that alone. The two laws contradict each other. The courtroom operates by switching between them at undefined moments. No one can say exactly when Law 1 ends and Law 2 begins. No one can say who decides. The system works. Verdicts are reached. Cases are resolved. But the foundation is incoherent. Copenhagen is this courtroom. Hugh Everett saw the contradiction, and in 1957, at the age of 26, he proposed the most radical solution imaginable. remove the collapse. Remove the Born rule as a postulate. Keep only the Schrödinger equation. Let it apply to everything: particles, detectors, observers, the entire universe, without exception, without interruption, without collapse. The consequence is immediate and devastating. If the Schrödinger equation applies to the observer, and the observer interacts with the system in superposition, then the observer enters a superposition too. The observer does not see one outcome. The observer splits, becoming entangled with the system, branching into multiple versions, each version seeing a different outcome. Each version is equally real. Each version continues to evolve according to the Schrödinger equation. Each version believes it saw a single, definite result. None of the versions can communicate with the others. The interference between branches is destroyed by decoherence, the process by which quantum coherence leaks into the environment, discovered by H. Dieter Zeh, born 1932, died 2018, German physicist, in 1970, and formalized by Wojciech Zurek, born 1951, Polish-American physicist at Los Alamos National Laboratory in the early 1980s. Everett wrote the mathematical relation that defines this picture. It is the third equation that matters. Ket capital psi equals sum over I of C sub I. Ket SI subscript S, tensor product. Ket AI subscript O. Capital psi is the universal wave function, the wave function of the entire universe. C sub I are the amplitudes, complex numbers whose squared magnitudes give the Born rule probabilities. Ket SI are the system states, the possible outcomes of the measurement. Ket A psi are the observer states, the correlated states of the observer. Each term in the sum is a relative state, the system state relative to a specific observer outcome. Each term, Everett argued, is a world. Every possible outcome is realized in some term. Every choice the universe could make, at every quantum event, at every measurement, at every interaction, is made. All of them, simultaneously, forever. Everett wrote in his thesis, "From the viewpoint of the theory, all elements of a superposition, all branches, are actual, none any more real than the rest." This is the many worlds interpretation. Every choice human is real. Every choice you did not make is also real in another branch of the universal wave function, where another version of you made that choice and is living that life, and believes, as you do, that they are the only version. What does it mean that the simplest possible interpretation of the most fundamental equation in physics, the interpretation that takes the equation literally, without additions, without modifications, without postulates, demands the existence of an uncountable infinity of parallel worlds? Before I continue, consider what this means. Take a moment. If the many worlds interpretation is correct, then every quantum event, every radioactive decay, every photon absorption, every molecular interaction splits the universe. not metaphorically, physically, the universal wave-function branches, and each branch is a complete, self-contained reality, with its own galaxies, its own stars, its own planets, its own observers, each as real as the room you are sitting in. The number of branches is not large, it is not astronomical. It is beyond any number that can be written, spoken, or conceived. 300 qubits span a Hilbert space of approximately 10 to the 90 dimensions, exceeding the number of atoms in the observable universe. The universal wave function operates in a Hilbert space of effectively infinite dimensions. The ontological cost of the many worlds interpretation is infinity. Now let us examine whether the price is worth paying, and whether the alternatives are any better. Decoherence, the process that makes the many worlds interpretation physically plausible, was the missing piece that connected Everett's abstract mathematics to observable reality. Without decoherence, Everett's theory predicts interference between branches, and we do not observe interference between macroscopic objects. Why do we not see pulses that are simultaneously alive and dead? Why do we not see measuring devices showing two readings at once? Why does the classical world appear so definite, so singular, so non-quantum? The answer, discovered by Zeh and formalized by Zurek, is environmental entanglement. When a quantum system interacts with its environment, with the photons scattering off it, the air molecules bouncing against it, the thermal radiation bathing it, the system becomes entangled with the environment. The entanglement causes the interference terms between different branches of the superposition to leak into the environmental degrees of freedom, becoming undetectable on timescales so short they defy comprehension. The Juzet decoherence timescales calculated in 1985 are staggering. For a dust grain approximately 10 micrometers in diameter in ordinary air at standard temperature and pressure, the decoherence time, the time for the interference between two position states to become undetectable, is approximately 10 to the negative 31 seconds. For comparison, the Planck time, the shortest meaningful time in physics, is approximately 5.39 times 10 to the negative 44 seconds. The decoherence is 10 trillion Planck times, and yet it is a tenth of a trillionth of a trillionth of a billionth of a second. The superposition of a dust grain being in two places is destroyed, for all practical purposes, faster than any physical process could detect it. For a large molecule in the best laboratory vacuum, the decoherence time is approximately 1 second, long enough for the interference to be observed, which is exactly what the experiments confirm. Marcus Arndt and colleagues in Vienna demonstrated interference of fullerene molecules, C60, 720 atomic mass units, 60 carbon atoms, in 1999, and in 2019, Yakov Fine and colleagues demonstrated interference of oligoporphyrin molecules exceeding 25,000 atomic mass units, approximately 2,000 atoms, with coherence times exceeding 7 milliseconds. The molecules behaved as waves. They interfered with themselves. They were in superposition, and when those molecules interact with their environment, with air, with light, with surfaces, the superposition is destroyed and the molecule behaves classically. Decoherence explains why we do not see macroscopic superpositions. It explains why cats are either alive or dead, never both. It explains why measurement devices show definite readings. It explains why the classical world looks classical. What decoherence does not explain is what happens to the other branches. In the Copenhagen interpretation, the other branches disappear. They collapse into non-existence, destroyed by the measurement. In the many worlds interpretation, the other branches persist. They decohere from our branch, becoming inaccessible, but they continue to exist and evolve according to the Schrödinger equation. The physical predictions are identical. No experiment can distinguish between the other branches were destroyed and the other branches still exist, but we cannot access them. The disagreement is not empirical. It is metaphysical. It is about what exists, not about what can be measured. The many worlds interpretation was resurrected from obscurity by Bryce DeWitt, born 1923, died 2004, American physicist at the University of North Carolina and later the University of Texas at Austin. In September 1970, DeWitt published Quantum Mechanics and Reality in Physics Today, coining the name Many Worlds and bringing Everett's ideas to a broad audience for the first time. In 1973, DeWitt and Neil Graham edited The Many Worlds Interpretation of Quantum Mechanics, Princeton University Press, which printed Everett's long thesis in full for the first time. The book transformed Many Worlds from a forgotten dissertation into a live contender in the Foundation's debate. In 1977, Wheeler and DeWitt invited Everett to give a talk at the University of Texas at Austin. In the audience was a young physicist named David Deutsch, born 1953, British-Israeli, later at Oxford. Deutsch would become the founder of quantum computing. In 1985, Deutsch published a paper describing the universal quantum Turing machine, the theoretical foundation of quantum computation. The paper was explicitly motivated by the many worlds interpretation. Deutsch argued that the exponential speed-up of quantum computers, the ability to perform certain calculations, such as Shor's algorithm for factoring large numbers, exponentially faster than any classical computer, constitutes evidence for the reality of many worlds. The quantum computer, Deutsch argued, computes in parallel across multiple branches of the universal wave function. The branches are real because the computation works. Think about this through an analogy. Picture a library with 1 million books. You need to find one specific sentence in one specific book. A classical search, reading one book at a time, requires, on average, checking 500,000 books. A quantum search, Grover's algorithm, requires checking only approximately 1,000. The speed-up is real. It has been demonstrated in laboratories around the world. Google's Sycamore processor, a 53-qubit quantum computer, performed a random circuit sampling task in October 2019 in 200 seconds that Google claimed would take the most powerful classical supercomputer approximately 10,000 years. IBM contested the claim, but the principle is established. Quantum computers perform certain tasks exponentially faster than classical computers. Deutsch's argument is provocative. Where does the computation happen? If the quantum computer is exploring only one branch, one configuration, how does it search 10 to the 90 possibilities simultaneously? Deutsch's answer: it searches them because they exist. The branches are real. The parallel computation occurs across real physical branches of the universal wave function. The prosecution: this argument is suggestive but not conclusive. The computation can be described without invoking many worlds, using the standard mathematical formalism of quantum mechanics, which all interpretations share. The exponential speedup follows from the mathematics of Hilbert space and unitary development. Copenhagen describes it as superposition and interference. Bohmian mechanics describes it as non-local pilot wave dynamics. Cubism describes it as optimal belief updating. The computational result is the same in every interpretation. The interpretation is underdetermined by the data. Think about this through another analogy. Picture two cartographers who produce identical maps of the same territory. Every road, every river, every contour line is the same. One cartographer says the territory contains hidden underground rivers that explain why the surface rivers flow the way they do. The other says no underground rivers exist. The surface rivers are self-explanatory. Both maps work. Both predict the same terrain. The disagreement is about what lies beneath the surface. No surface measurement can resolve it. What does it mean that the most powerful argument for the physical reality of many worlds, the exponential speedup of quantum computing, is equally well described by every competing interpretation? This brings us to the specific problems with the many worlds interpretation, the problems that its proponents acknowledge and cannot solve. The pilot wave theory, proposed by Louis de Broglie in 1927, born 1892, died 1987, French physicist, Nobel Prize, 1929, and revived by David Bohm in 1952, born 1917, died 1992, American physicist, offers a fully deterministic alternative. In Bohmian mechanics, particles have definite positions at all times, guided by a pilot wave, the wave function, through a guiding equation. The fourth equation, dq minus k by dt equals h bar over m minus k, imaginary part of gradient minus kpi divided by psi. Every outcome is determined by the initial positions of all particles, positions that, in Bohm's framework, were set at the beginning of the universe. There is no collapse. There is no randomness. There is one world with definite particle positions guided by a universal wave function. The theory reproduces all predictions of quantum mechanics. It is explicitly non-local, a feature confirmed by John Bell's theorem, 1964, and the loophole-free Bell tests of 2015. In October 2015, Ronald Hansen and colleagues at the Delft University of Technology measured entangled nitrogen vacancy centers in diamond separated by 1.3 kilometers and found a CHSH violation of S equals 2.42, plus or minus 0.20. In November 2015, Marissa Justina's team in Vienna achieved a violation with a statistical significance of 11.5 sigma, a probability of error less than 3.74 times 10 to the negative 31. In the same month, Lyndon Shalm and colleagues at NIST closed remaining loopholes across 185 meters. In June 2017, the Messius satellite distributed entanglement over 1,203 kilometers between ground stations in China, measuring S equals 2.37 plus or minus 0.09. Local realism, the common-sense view that objects have definite properties independent of measurement and that influences travel no faster than light, is empirically dead. The 2022 Nobel Prize in Physics was awarded to Alain Aspect, John Clauser, and Anton Zeilinger for this work. Bohmian mechanics accepts the non-locality explicitly. It pays a different price: inelegance. The guiding equation is an addition to the Schrödinger equation, an extra piece of mathematical machinery that the Schrödinger equation does not require. The particle positions are hidden variables. They cannot be directly observed, only inferred from measurement outcomes. The theory preserves one world at the cost of adding structure that the fundamental equation does not contain. Sean Carroll, born 1966, American physicist, leading defender of many worlds, author of Something Deeply Hidden, 2019, has called this adding epicycles to save the phenomena. The GRW model, proposed by Giancarlo Ghirardi, Alberto Rimini, and Tullio Weber in 1986, all Italian physicists, modifies the Schrödinger equation itself. GRW adds spontaneous random collapses, localization events that affect each particle with a tiny probability, approximately 10 to the negative 16 per second per particle, and a localization width of approximately 10 to the negative 5 centimeters. For a single particle, this is negligible. For a macroscopic object containing 10 to the 23 particles, at least one particle localizes per nanosecond, dragging the entire object into a definite state. GRW produces one world by modifying the fundamental equation, by adding new physics that has never been observed and that is increasingly constrained by experiment. The 2019 Fine experiment, demonstrating interference of 25,000 Dalton molecules, ruled out large regions of GRW parameter space. The theory remains speculative. Roger Penrose, born 1931, British mathematical physicist, Nobel Prize 2020, proposes a different collapse mechanism: gravitational objective reduction, in which superpositions of different space-time geometries trigger collapse at a timescale determined by the gravitational self-energy difference. Penrose's model is elegant but unconfirmed. No experimental test has validated it. It requires new physics beyond the standard model, physics that may or may not exist. Relational quantum mechanics, proposed by Carlo Rovelli in 1996, born 1956 Italian physicist, takes a different approach entirely. Rovelli argues that quantum states are relational. They exist only relative to a specific observer. There is no observer-independent wave function. There is no universal wave function. There is no view from nowhere. Each observer has a valid description of reality, and different observers may disagree about the state of a system, with both being correct relative to their own interactions. Rovelli's view is philosophically radical. It abandons the idea of an objective, observer-independent reality, but it preserves one world. The price is that reality becomes perspectival. What exists depends on who is asking. Think about this through an analogy. Picture two people standing on opposite sides of a mountain. One sees the north face, snow-covered, sheer, forbidding. The other sees the south face, grassy, gentle, sunlit. Both descriptions are accurate. Both are incomplete. Neither sees the whole mountain. Rovelli's quantum mechanics says there is no whole mountain. There are only perspectives. The north face and the south face are not partial views of a deeper reality. They are all the reality there is. There is no mountain apart from the viewing. Consistent histories, developed by Robert Griffiths, born 1937, American physicist at Carnegie Mellon, 1984, Roland Omnes, French physicist, and Murray Gell-Mann with James Hartle, offers yet another approach. Consistent histories treats quantum mechanics as a calculus over histories, sequences of events satisfying mathematical consistency conditions. In this framework, you can assign classical-like probabilities to sequences of events without invoking collapse. The approach is technically close to many worlds, but philosophically single world. Only one history is actualized, though the theory does not specify which. The main critique, raised by Faye Dowker and Adrian Kent in 1996, is that the choice of consistent set is not unique. Different choices lead to incompatible descriptions of the same physical situation. The framework describes but does not determine. The von Neumann-Wigner interpretation, endorsed by a small minority, approximately 6% in the Schlosshauer 2013 poll n equals 33, proposes that consciousness causes collapse. When a conscious observer becomes aware of a measurement result, the wave function collapses. This view was inspired by John von Neumann's 1932 formalization of collapse and Eugene Wigner's philosophical reflections. It is largely rejected today as scientifically untenable. It gives consciousness a physical role that no equation describes and no experiment supports. The many worlds interpretation was explicitly designed to remove consciousness from the physics. Everett's innovation was precisely this. The observer is a quantum system like any other, with no special role, no privileged status, no collapse-inducing awareness. The observer simply branches. Each interpretation pays a price. Copenhagen pays with incoherence, two incompatible dynamics and an undefined measurement boundary. Many worlds pays with infinity, an uncountable number of unobservable parallel realities. Bohmian mechanics pays with inelegance, hidden variables, and non-local guidance. GRW pays with speculation, modified equations, and untested physics. Relational QM pays with relativism, no observer-independent reality. Consistent histories pays with ambiguity, non-unique consistent sets. Von Neumann-Wigner pays with mysticism, consciousness as a physical force. Cubism pays with subjectivism, quantum states as beliefs, not descriptions of reality. No interpretation is free. Every interpretation adds something to the Schrödinger equation or subtracts something from our conception of reality. The measurement problem remains, not because physicists are not clever enough to solve it, but because the problem may be pointing to something outside the framework of physics itself. The existential implications of the many worlds interpretation deserve examination because they reveal with unusual clarity what the theory demands of anyone who accepts it. Quantum immortality, first described in a 1998 thought experiment by Max Tegmark, born 1967, Swedish-American physicist at MIT, follows from the many worlds interpretation with disturbing logical consistency. If every quantum outcome is realized in some branch, and if a person's death depends on a quantum event, then the person always survives in some branch. The branches where they die continue without them. The branches where they survive continue with them. From the subjective perspective of the survivor, they never die, because every branch in which they would die is a branch they are not in. Tegmark described the thought experiment in terms of a quantum suicide machine, a gun triggered by a quantum random number generator. Press the trigger, and the quantum event determines whether the gun fires. In many worlds, both outcomes occur. In one branch the gun fires and you die. In another branch the gun does not fire and you survive. Press the trigger again. Same result. Again. Again. After 1,000 presses, in some branches you are dead 1,000 times over. In one branch you have survived 1,000 trials. If you are that survivor, you experience 1,000 miraculous escapes, a run of luck so improbable that it constitutes, from within many worlds, subjective evidence that the theory is correct. Tegmark himself has partly walked back the thought experiment. He now notes that death is typically a gradual process. Without a clean quantum branching point, consciousness fades. Neurons degrade. Organ systems fail in continuous thermal, effectively classical processes. Deutsch rejects quantum immortality entirely. The thought experiment remains, however, as a logical consequence of the many worlds framework, and as a vivid illustration of what the theory implies about the nature of personal identity and subjective experience. Everett himself believed in quantum immortality. According to his biographer Eugene Shikovtsev, Everett discussed Russian roulette variants of the thought experiment with colleagues and privately believed that his consciousness would always follow a surviving branch. He died of a heart attack at 51, an event caused not by a discrete quantum trigger, but by decades of obesity, alcoholism, and chain smoking. The irony is precise. The man who believed his theory guaranteed him subjective immortality, destroyed his body through lifestyle choices whose consequences are thermodynamic, not quantum. What does it mean that the inventor of the many worlds interpretation believed his theory guaranteed him immortality and died at 51 from the cumulative effect of choices the theory says are irrelevant to the question of survival? The Boltzmann brain problem is related and equally devastating. Cubism holds that quantum states are not descriptions of reality at all. They are descriptions of an agent's beliefs, degrees of confidence about future measurement outcomes. The Born rule is not a law of nature. It is a normative rule, a guide for rational belief updating. There is no wave function out there. There is only your belief about what will happen when you measure. Fuchs has dismissed the many worlds interpretation with characteristic bluntness, calling it trying to regrow a lizard from the tip of its chopped-off tail. What does it mean that after nearly a century of debate, after thousands of papers, hundreds of books, dozens of conferences, and the combined intellect of the greatest physicists in history, there is no consensus on what quantum mechanics means? No agreement on whether the wave function is real or epistemic? No agreement on whether collapse happens or does not happen? No agreement on whether other worlds exist or do not exist? Steven Weinberg, one of the greatest physicists of the 20th century, Nobel Prize 1979, atheist, stated, "It is a bad sign that those physicists today who are most comfortable with quantum mechanics do not agree with each other about what it all means." Richard Feynman, born 1918, died 1988. American physicist, Nobel Prize, 1965, stated, "I think I can safely say that nobody understands quantum mechanics." Earlier in the same book, The Character of Physical Law, MIT 1965, Feynman added, "Nobody knows how it can be like that." N. David Mermin, born 1935, American physicist at Cornell, coined the phrase that defined a generation's attitude toward the measurement problem: "Shut up and calculate." Published in Physics Today in April 1989, the phrase captured the pragmatic instrumentalism that allowed physicists to use quantum mechanics without understanding it. Mermin later acknowledged that the phrase oversimplified the situation and eventually became a convert to Cubism, the subjective Bayesian interpretation developed by Fuchs. John Archibald Wheeler, Everett's own advisor, captured the depth of the paradox with characteristic precision. Each of us, a private universe? Preposterous! Each of us see the same universe? Also preposterous! Wheeler supported Everett's mathematics but recoiled from its ontological implications. His later work, The Participatory Universe and It from Bit, reflected a lifelong attempt to find a middle path between Copenhagen's incoherence and many worlds' excess. The survey data confirms the disagreement. A 2013 poll conducted by Schlosshauer, Kofler and Zeilinger at a Quantum Foundations conference in Vienna, sample size n equals 33, found Copenhagen, 42% information-based interpretations, 24%, Everett 18%, objective collapse 9%, cubism 6%, relational QM 6%, Bohmian mechanics 0%. A larger 2016 survey by Sivasundaram and Nielsen, n equals 149, found Copenhagen 39%, Everett 6%, Bohmian 2%, no preference 36%. A 2025 Nature Centennial survey found Copenhagen at 36%, still leading but weakening. Among foundations, researchers specifically, only 20% chose Copenhagen. The numbers confirm what Weinberg diagnosed. Those most comfortable with quantum mechanics do not agree on what it means. The disagreement is not academic. It is about what exists. It is about whether the wave function is real or epistemic, whether collapse happens or does not happen, whether other worlds exist or do not exist, whether consciousness plays a role or does not play a role, whether quantum mechanics describes the world or merely our beliefs about the world. These are the deepest questions in physics, and after a century, they are unanswered. I return to this point often, not because it is comfortable, because it is diagnostic. The most successful physical theory in history, confirmed by every experiment used in every technology, from lasers to transistors to MRI machines to quantum computers, cannot explain its own meaning. The theory works. The theory is silent about why it works, what it describes, and what exists. This silence is not a minor gap. It is the deepest unresolved question in all of physics, and it points, as we will see, in a direction that the physics community has been reluctant to follow. Now, let us examine the specific problems with the many worlds interpretation, the problems that its proponents acknowledge and cannot solve. The probability problem. In the many worlds interpretation, every outcome occurs. There is no randomness. The universal wave function evolves deterministically. Every branch exists with certainty. If every outcome occurs, what does probability mean? Why do we observe outcomes with frequencies that match the Born rule? Why does the electron spin up approximately half the time and down approximately half the time, if both outcomes occur in every experiment? This is not a minor objection. It is the central technical challenge facing many worlds. David Deutsch, born 1953, British-Israeli physicist at Oxford, founder of quantum computing, 1985, proposed a decision-theoretic derivation of the Born rule in 1999, arguing that a rational agent in a branching universe should weight their decisions by the squared amplitudes. David Wallace, British philosopher of physics, author of The Emergent Multiverse, Oxford University Press, 2012, formalized this argument axiomatically. Zurek proposed an alternative derivation through invariance, environment-assisted invariance, in 2003 and 2005. Sean Carroll and Charles Sebens proposed a self-locating uncertainty derivation in 2018. Each derivation has attracted serious technical objections. Adrian Kent, British physicist at Cambridge, the most rigorous critic of many worlds, argued that the decision-theoretic approach assumes what it needs to prove: that rational agents should care about branches in proportion to their squared amplitudes, rather than simply counting branches. David Albert, American philosopher at Columbia, raised the fatness objection. Why should you weight the branches you care about by their amplitude rather than by their number? Tim Maudlin, American philosopher at NYU, argued that wavefunction monism is epistemically incoherent. A high-dimensional mathematical object in Hilbert space cannot straightforwardly ground the low-dimensional macroscopic experience of three-dimensional beings. What does it mean that the many worlds interpretation, the interpretation that claims to be the simplest, the most parsimonious, the most natural reading of the Schrödinger equation, cannot derive the Born rule without, assumptions that its critics consider question-begging, the preferred basis problem? In the many worlds interpretation, the universe branches. But into what? What determines the basis, the set of states along which the branching occurs? Why does the universe branch into cat alive and cat dead, rather than into some other physically meaningless combination of those states? The answer, provided by decoherence and einselection, Zurek's environment-induced superselection, is that the environment selects a preferred basis, the pointer states, that are stable under environmental interaction. The pointer states are the eigenstates of the system-environment interaction, Hamiltonian. They are the states that survive decoherence. All others are destroyed. This answer is powerful and experimentally supported. It is also, critics argue, insufficient. The environment selects the basis, but the environment is itself a quantum system, described by the universal wavefunction. The preferred basis is defined by the environment's structure. But the environment's structure is, in many worlds, itself branching. The circularity is subtle but persistent. Sabine Hossenfelder, German physicist, author of Lost in Math 2018, stated, "The problem with many worlds is that you have to add an assumption to explain what we observe. You need a rule that tells you which branch you are in." The initial state problem, the many worlds interpretation, assumes the existence of the universal wave function. It assumes the Schrödinger equation governs its development. It does not explain why the universal wave function exists, why it has the specific initial state it has, or why the Schrödinger equation holds. The theory explains measurements. It does not explain existence. Think about this through an analogy. Picture a mathematician who discovers a formula that perfectly predicts the trajectory of every projectile ever launched, every ball, every bullet, every rocket. The formula works. It has never failed. The mathematician is asked, where does the formula come from? Why does it work? Why this formula and not some other? The mathematician has no answer. The formula describes the behavior. It does not explain the behavior. The map is perfect. The territory remains mysterious. What does it mean that the many worlds interpretation, the interpretation that claims to explain quantum mechanics by taking the equations seriously, cannot explain why the equations exist, why they have the form they have, or why the initial state of the universe was what it was? This is where the apologetic question becomes unavoidable. The many worlds interpretation, if taken literally, asserts the existence of an infinite number of parallel realities, each as real as ours, each containing complete copies of the cosmos, each inaccessible in principle to every other. This is the most extravagant ontological claim in the history of physics. It is also, by the theory's own admission, untestable. No experiment can detect another branch. No observation can confirm or deny the existence of parallel worlds. The theory is empirically equivalent to Copenhagen, to Bohmian mechanics, to consistent histories, to every other interpretation of quantum mechanics. George Ellis, South African cosmologist, former president of the International Society for General Relativity and Gravitation, stated in Scientific American, "All the parallel universes lie outside our horizon and remain beyond our capacity to see, now or ever, no matter how technology evolves." Ellis and Joe Silk wrote in Nature, 2014, that theories exempt from experimental verification undermine science. Paul Davies, British-Australian physicist and cosmologist, stated in the New York Times, April 12, 2003, "Extreme multiverse explanations are reminiscent of theological discussions, invoking an infinity of unseen universes to explain the unusual features of the one we do see is just as ad hoc as invoking an unseen creator. The multiverse theory may be dressed up in scientific language, but in essence, it requires the same leap of faith." Think about that admission. An infinity of unseen universes requires the same leap of faith as an unseen intelligent cause. The difference, which Davies does not state, but which the evidence makes clear, is that the intelligent cause explains the fine-tuning, the initial conditions, the existence of the Schrödinger equation, and the origin of the universe. The multiverse explains none of these. The multiverse is an escape route, an attempt to avoid the implications of fine-tuning by postulating an infinity of unobservable alternatives. The cosmological constant, lambda, is approximately 10 to the negative 122 in Planck units. The naive quantum field theory prediction exceeds the observed value by approximately 120 orders of magnitude. Steven Weinberg, one of the greatest physicists of the 20th century, Nobel Prize 1979, stated, "The existence of life of any kind seems to require a cancellation between different contributions to the vacuum energy, accurate to about 120 decimal places. 120 decimal places. Picture a number with 120 zeros after the decimal point and a single digit at the end, and that digit must be exactly right. A cancellation this precise, occurring by accident, is not improbable. It is, by any rational standard, impossible without specification. Roger Penrose, born 1931, British mathematician and physicist, Nobel Prize 2020, calculated the probability of the universe's initial entropy state at approximately 1 in 10 to the power of 10 to the 123. He described this in The Road to Reality as an absurdly tiny volume of phase space. One could not possibly even write the number down in full in the ordinary denary notation. It would be 1 followed by 10 to the 123 successive zeros. Writing this number, just writing it, would require more digits than there are particles in the observable universe. Martin Rees, born 1942, British cosmologist, Astronomer Royal, former president of the Royal Society, identified 6 dimensionless constants in his 1999 book, Just 6 Numbers, whose values must lie in narrow ranges for stars, chemistry, and observers to exist. The ratio of electromagnetic to gravitational force strength, approximately 10 to the 36. If significantly different, no stable stars. The nuclear binding efficiency, 0.007. The fraction of mass converted to energy when hydrogen fuses to helium. If this were 0.006, no carbon. If 0.008, no hydrogen. The cosmic density parameter omega, approximately 1. The universe is flat to extraordinary precision. The cosmological constant lambda. The density fluctuation amplitude q, approximately 10 to the negative 5. If larger, the universe would have collapsed into black holes. If smaller, no galaxies, no stars, no planets. The number of spatial dimensions, exactly 3 in 2 dimensions, no complex structures, in 4 or more, no stable orbits. Fred Hoyle, born 1915, died 2001, British astronomer, discovered that carbon nucleosynthesis in stars requires a specific nuclear resonance, the Hoyle state at approximately 7.65 mega-electron volts, to produce carbon in sufficient quantities. Without this resonance, the triple alpha process would be too slow, and the universe would contain almost no carbon, the element on which all known life depends. Hoyle stated, "A common-sense interpretation of the facts suggests that a super-intellect has monkeyed with physics, as well as with chemistry and biology, and that there are no blind forces worth speaking about in nature. The numbers one calculates from the facts seem to me so overwhelming as to put this conclusion almost beyond question." The Higgs hierarchy problem adds another layer. The electroweak scale is approximately 246 giga-electron volts, while the Planck scale is approximately 10 to the 19 giga-electron volts, a ratio of approximately 10 to the 17 in mass. quantum corrections to the Higgs boson mass should drive it toward the Planck scale, but the observed Higgs mass, approximately 125 giga-electron-volts, confirmed at the Large Hadron Collider at CERN in July 2012, sits far below. The stability of the electroweak scale requires a cancellation between quantum contributions that individually scale as 10 to the 34 in mass squared to produce a net value 34 orders of magnitude smaller. No natural explanation for this cancellation has been found. Picture a combination lock with 26 dials. Each dial runs from 0 to a trillion. The lock opens only when all 26 are set to specific values, not approximately exactly. The probability of hitting the right combination at random is a number with no useful analogy. What makes this stranger than any combination lock? The dials were not set by anyone turning them. They appear to have come preset from the beginning of time. The question is not whether the combination was set. The question is whether it was set by accident or by intention. Now consider the many worlds. Interpretations branching occurs within a single set of physical laws. MWW. I branches do not vary the fundamental constants. MWI does not produce universes with different gravitational constants, different electromagnetic strengths, different cosmological constants. The branching preserves the laws. It multiplies the outcomes. The fine-tuning of the laws themselves, the specific values of alpha, lambda, the strong force coupling, the Higgs mass, is not addressed by many worlds branching at all. To address fine-tuning, you need Max Tegmark's Level 2 multiverse, different physical constants, or Level 4, different mathematical structures. Separate hypotheses, with their own evidential burdens, their own unfalsifiability, their own infinite ontological commitments. What does it mean that the many worlds interpretation, the interpretation invoked to explain quantum measurements, does not even address the fine-tuning of the physical constants it assumes? The Boltzmann brain problem adds another dimension. In any generic multiverse, whether many worlds branching or cosmological bubble nucleation, random thermal fluctuations should produce isolated momentary conscious brains, Boltzmann brains, that briefly flicker into existence with fabricated memories and then dissolve. In a generic multiverse, Boltzmann brains vastly outnumber embodied observers in 13.8 billion-year-old ordered cosmoi like ours. If the multiverse is the explanation for fine-tuning, we should expect to be Boltzmann brains, random fluctuations with false memories. We are not. We observe an ordered cosmos. Our memories are consistent with 13.8 billion years of cosmic history, confirmed by the cosmic microwave background, primordial nucleosynthesis, and the observed expansion. Sean Carroll himself acknowledged the Boltzmann brain problem. They constitute a reductio ad absurdum. Think about this through an analogy. Picture a factory that produces random assemblages of components, gears, springs, transistors, wires, billions per second, for billions of years. Occasionally, by chance, a functioning watch emerges. Far more often, overwhelmingly more often, random assemblages produce something that briefly resembles a watch, showing the correct time for 1 second before falling apart. If you find yourself holding a watch that appears to have been working for years, you have two options. Option 1, you are holding a real watch assembled by a watchmaker. Option 2, you are a Boltzmann fluctuation who only believes the watch has been working for years. Your memory of the watch is fabricated along with the watch itself. The multiverse, taken seriously, makes option 2 overwhelmingly more probable. The fact that option 1 appears to be correct is evidence against the multiverse as an explanation, and evidence for a watchmaker. This is the part that stays with me, not the mathematics, though the mathematics is precise. Not the experiments, though the experiments are definitive. The explanatory bankruptcy. The many worlds interpretation eliminates the measurement problem by postulating an infinity of unobservable worlds. It does not explain why the Schrödinger equation exists. It does not explain why the Born rule holds. Its derivations are contested. It does not explain the fine-tuning of the constants. It does not explain the initial state of the universal wave function. It does not explain consciousness, the subjective experience of being in one branch rather than another. It does not explain why the universe exists at all. It multiplies what it cannot explain. It is ontologically maximal and explanatorily minimal. The materialist claim that science will eventually explain it is not an argument. It is faith. Faith in future discoveries deployed to avoid a present conclusion. The gaps in the many worlds interpretation are not gaps in data. They are gaps in explanatory structure. Why does the Schrödinger equation exist? Why Hilbert space? Why these Hamiltonians? Why this initial state? These are not questions that more experiments will answer. These are questions about the existence of the framework itself, and no framework explains its own existence. Eugene Wigner, born 1902, died 1995. Hungarian-American physicist, Nobel Prize, 1963, stated in his celebrated 1960 essay, "The Unreasonable Effectiveness of Mathematics in the Natural Sciences." The miracle of the appropriateness of the language of mathematics for the formulation of the laws of physics is a wonderful gift, which we neither understand nor deserve. Wigner called it a miracle, not casually, not poetically, as a term of precise philosophical description. The Schrödinger equation, a single mathematical expression involving complex numbers, operators on an infinite dimensional Hilbert space, and the imaginary unit, describes every quantum system in the universe with extraordinary accuracy. Why? Why does this equation work? Why does mathematics, a human invention, or perhaps a human discovery, map onto the physical world with such unreasonable precision? Think about this through an analogy. Picture a locksmith who discovers that a key he carved from a dream, a key shaped by nothing but imagination, opens every lock in a city he has never visited. The locksmith did not design the key for those locks. The key was not based on measurements of those locks. The match between key and lock is perfect, complete, and unexplained. The Schrödinger equation is the key. The physical universe is the city. The match between them is Wigner's miracle, and no naturalistic account has explained it. The many worlds interpretation magnifies Wigner's miracle rather than diminishing it. If the universal wave function evolving according to a single equation in a Hilbert space of infinite dimensions generates all of physical reality, every particle, every interaction, every branch, every world, then the structural precision of the equation is not merely impressive. It is the most extraordinary instance of specified complexity in the history of science. A single mathematical object, I who ch bar partial psi by partial t equals h hat psi, encodes the complete dynamics of reality. The equation was not derived from any deeper theory. It was discovered by Erwin Schrödinger in 1926 through a combination of physical intuition and mathematical experimentation. Its existence is a brute fact. Its precision is unexplained. Its power is, by any rational assessment, suggestive of a designing intelligence. Freeman Dyson, born 1923, died 2020, British-American physicist and mathematician, stated, "The more I examine the universe and study the details of its architecture, the more evidence I find that the universe in some sense must have known that we were coming." Albert Einstein, in a letter to Max Born on December 4, 1926, wrote, "Quantum mechanics is certainly imposing, but an inner voice tells me that it is not yet the real thing. The theory says a lot, but does not really bring us any closer to the secret of the old one. I, at any rate, am convinced that he does not throw dice." Einstein was right about the dice, but not in the way he expected. The many worlds interpretation eliminates the dice. The Schrödinger equation is deterministic. There is no randomness. There is no collapse. There is only the universal wave function, evolving inexorably according to a single equation, branching into every possibility, with no choice, no selection, no preference. The dice are not thrown. Every face lands. Every outcome occurs. What does it mean that eliminating the randomness from quantum mechanics does not produce order? It produces infinity. What does it mean that the price of determinism is an uncountable multiplicity of worlds? The consciousness question is directly relevant. In the many worlds interpretation, the observer branches. The you who sees spin up is one copy. The you who sees spin down is another copy. Each copy experiences one definite outcome. Each copy has a subjective sense of being the only you. But the many worlds interpretation does not explain why there is a subjective experience at all. The branching is described by the Schrödinger equation, a deterministic, impersonal, mathematical development. The equation does not predict consciousness. It does not contain consciousness. It would operate identically in a universe of philosophical zombies, beings physically identical to us, but with no inner experience. Materialists claim consciousness is merely brain activity, that neurons firing in certain patterns produce subjective experience. The prosecution, neuroscience can correlate brain states with mental states, but it cannot explain how physical processes produce the qualitative experience of being aware. The hard problem of consciousness, identified by David Chalmers in 1995, remains unsolved. Atoms have no awareness. Molecules have no thoughts. No arrangement of unconscious particles has been shown to produce subjective experience through any known mechanism. If consciousness is not derived from physics, and the equations of physics do not contain it, then consciousness points beyond the physical framework. It points to something non-material. It points to an intelligent cause that endowed material beings with the capacity for awareness. The moral implications of many worlds deserve examination. If the many worlds interpretation is correct, then every moral choice you have ever made has a shadow version in another branch where you made the opposite choice. In some branch, you were kind. In another, you were cruel. In some branch, you helped. In another, you harmed. Every act of courage has a cowardly counterpart. Every act of honesty has a deceptive twin. If every choice is made, if every possibility is realized, then moral responsibility, as ordinarily understood, is threatened. What does it mean to be responsible for a choice if the opposite choice was also made by another equally real version of you in another equally real branch? Carroll has argued that each branch self remains responsible within its branch, that moral responsibility does not require uniqueness. This may be coherent. It is also thin. The weight of moral choice, the gravity of knowing that you could have done otherwise, depends on the reality of the alternative. If the alternative is real, if the other version of you really did do otherwise, then the sense in which your choice was meaningful is diminished. Not eliminated, diminished. The moral landscape becomes a field of actualities rather than possibilities, and the difference between what you did and what you could have done collapses into the fact that both were done. Think about what this means. Take a moment. If every choice is made, then the concept of choosing is redefined. Choice, in the ordinary sense, means selecting one option from among alternatives. In many worlds, there is no selection. There is only branching. The you who chose kindness did not reject cruelty. Another you chose cruelty. The decision was not made. The split was made. And the split was not made by you. It was made by the Schrödinger equation, by the deterministic, impersonal, unconscious mathematics of quantum development. This brings us to the question that the physics cannot answer, the question that the many worlds interpretation, with all its mathematical elegance and ontological extravagance, leaves entirely open. Something has always existed. If there were ever truly nothing, no wave function, no Hilbert space, no Hamiltonian, no mathematical structure, no potential, no possibility, then nothing would exist now. Nothing has no mechanism. Nothing has no tendency. 0 plus 0 equals 0. The universe exists. The Schrödinger equation holds. Quantum mechanics works. Something has always existed. The universe itself has not always existed. The Big Bang, confirmed by the cosmic microwave background, Penzias and Wilson, 1965, COBE, 1992, WMAP, 2003, Planck, 2018, the observed expansion, Hubble, 1929, supernova teams, 1998, Nobel Prize, 2011, and the Bordeguth-Vilenkin theorem, 2003, establishes a finite past. Whatever caused the universe must be external to it, external to time, space, the Schrödinger equation, and the Hilbert space in which the universal wave function evolves. Whatever caused the universe must possess specific attributes, deduced from the evidence, not assumed by theology. Power sufficient to bring into existence the universal wave function, the Hilbert space it inhabits, the Schrödinger equation that governs it, and the initial state from which all branching proceeds. If many worlds is correct, the cause brought into existence not one universe, but every possible universe, every branch, every configuration, every outcome. The power required is beyond comprehension. Knowledge sufficient to configure the physical constants within the narrow life-permitting ranges. The fine structure constant at 1/137. The cosmological constant at 10 to the negative 122 in Planck units. The strong force tuned to within 2%. The proton-to-electron mass ratio at 1836.15. The density fluctuation amplitude at 10 to the negative 5. The number of spatial dimensions at exactly 3. These values are not varied by many worlds branching. They are inputs to the Schrödinger equation, initial conditions that the equation requires but does not derive. Selection from a vast space of alternatives requires knowledge of the alternatives and their consequences. Will, because a specific set of laws, a specific equation, a specific initial state was selected. The Schrödinger equation could have been a different equation. Hilbert space could have had a different structure. The Hamiltonians could have been different. They are what they are because something selected them. Selection from alternatives is an act. Acts require agents. Agents that select possess will. These attributes, power, knowledge, will, are the attributes of an intelligent cause, eternal, uncaused, distinct from the creation, not bound by the Schrödinger equation which it established, not contained in the Hilbert space which it brought into existence, not subject to decoherence, which operates on systems within the universe, not on the cause of the universe. The chain of causes must terminate. An infinite regress of dependent causes, each requiring a prior cause, stretching backward without limit, would never reach the present. The universe exists. The Schrödinger equation holds. The wave function evolves, the branches proliferate. The fact that any of this is happening proves the chain terminates at something uncaused, something eternal, self-sufficient, and intelligent. What does it mean that the many worlds interpretation, The interpretation that posits an infinity of worlds to explain quantum measurements cannot explain why any world exists at all. What does it mean that the most extravagant ontology in the history of science leaves the most fundamental question unanswered? It means the evidence points one direction, not toward the multiverse as a final answer, because the multiverse does not answer. It multiplies. It proliferates. It inflates. It does not explain. The evidence points toward an intelligent cause with power, knowledge, and will that brought the universal wave function into existence, configured the Schrödinger equation, set the initial conditions, and established the physical constants within the narrow ranges that permit chemistry, stars, planets, life, and conscious beings capable of discovering the equation and debating its interpretation. Let me bring this exploration to a close. We began with Hugh Everett III, a 27-year-old Princeton graduate student who, in 137 typewritten pages, proposed the most radical solution to the measurement problem in the history of physics. We traced his biography from the sherry-fueled conversation at Princeton in 1954, through the composition of the long thesis in 1955 to 56, the hostile reception in Copenhagen, Alexander Stern's dismissal as theology, Wheeler's cautious companion paper, the defense on April 23, 1957, the 6 futile weeks at the Hotel Oosterpoort in Copenhagen in 1959, the departure from physics, the Pentagon career, Lambda Corporation, the heavy drinking, the chain smoking, the heart attack at 51 on July 19th, 1982, and the ashes placed in the garbage per his instructions. We traced the family tragedy, Liz Everett's suicide in 1996, her note requesting her ashes be thrown out so she could end up in the correct parallel universe to meet up with Daddy, Nancy Everett's death from lung cancer in 1998, on what would have been Hugh's 68th birthday, Mark Everett's 2007 documentary, Parallel Worlds, Parallel Lives. The family that invented the multiverse was consumed by this one. We examined the measurement problem, the contradiction between the deterministic Schrödinger equation and the probabilistic Born rule, the undefined Heisenberg cut, the incoherence of Copenhagen's two-tier dynamics. We examined Schrödinger's cat, alive and dead simultaneously in the wave function, never observed in superposition. We examined the Wheeler delayed choice experiment, Jacques, 2007, the photon's history determined retroactively by a measurement choice. We examined the Kim quantum eraser, 2000, interference reappearing when which path information is erased. We examined Everett's solution, remove the collapse, keep only the Schrödinger equation, and accept that the observer branches, splitting into multiple versions, each seeing a different outcome, each equally real, each evolving deterministically. We stated the defining equation, ket capital psi equals the sum over I of c sub I. Ket si subscript s, tensor product. Ket ai subscript o, the relative state expansion, each term a world. We examined decoherence, Zay's 1970 discovery, Zureck's formalization of einselection in the early 1980s, the Juice-Zay timescales of 10 to the negative 31 seconds for a dust grain in air. We examined the experimental confirmations, Tonomura's single electron double-slit buildup, 1989, Arndt's C60 fullerene interference in Vienna, 1999, Fine's 25,000 Dalton molecular superposition, Vienna, 2019, the loophole-free Bell tests of 2015, Delft, Vienna, NYST, the Mickey's satellite entanglement over 1,203 kilometers, 2017, the Nobel Prize in Physics awarded to Aspect, Clauser and Zeilinger in 2022. We examined DeWitt's 1970 popularization of many worlds in physics. Today, the 1973 Princeton anthology and Deutsch's argument that quantum computing constitutes evidence for branching, an argument we showed to be suggestive but not conclusive, since the computational speed-up is equally described by every interpretation. We examined the competing interpretations, Copenhagen's postulated collapse, Bohmian mechanics' hidden variables, GRW's modified dynamics, Penrose's gravitational reduction, Ravelli's relational states, consistent histories' ambiguous sets, von Neumann-Wigner's consciousness-based collapse, Kubism's subjective beliefs, and showed that each pays a price, each leaves questions unanswered, and none can be empirically distinguished from the others. We examined the specific problems with many worlds, the probability problem, Born rule derivations contested by Kent, Albert and Maudlin, the preferred basis problem, Hossenfelder's circularity critique, the initial state problem, why the universal wave function exists at all. We examined quantum immortality, Tegmark's 1998 thought experiment, Everett's private belief in subjective survival across branches, the irony of his death at 51 from cumulative lifestyle destruction. We examined the Boltzmann brain problem, the reductio that generic multiverse reasoning predicts we should be random thermal fluctuations rather than embodied observers in an ordered cosmos. We examined the fine-tuning of physical constants, the cosmological constant at 10 to the negative 122, Weinberg's 120 decimal place cancellation, Penrose's entropy probability at 1 in 10 to the power of 10 to the 123, the Rees 6 numbers, the Hoyle resonance for carbon, the Higgs hierarchy problem, and showed that many worlds branching does not vary these constants and therefore does not address the fine-tuning. We examined the admissions of secular scientists. Weinberg, acknowledging the pointlessness the physics suggests, Davies calling the multiverse the same leap of faith, Wigner marveling at the unreasonable effectiveness of mathematics, Dyson finding evidence the universe must have known we were coming, Hoyle concluding that our super-intellect has monkeyed with physics, Einstein insisting that God does not throw dice. We examined the moral implications, the threat to moral responsibility when every choice is made in some branch, when the distinction between what you did and what you could have done collapses into the fact that both were done. We examined the consciousness question, the hard problem, the absence of consciousness from any physical equation, the many worlds, interpretation's inability to explain why branching produces subjective experience at all. Every line of evidence converges. The Schrödinger equation is precise beyond comprehension, a single mathematical expression generating the dynamics of all reality. The constants are fine-tuned beyond accident. The cosmological constant, the nuclear binding efficiency, the density fluctuation amplitude, the spatial dimensionality, each within a narrow window that permits chemistry, stars, planets, life, and conscious beings. The initial conditions are specific beyond chance. Penrose's 10 to the power of 10 to the 123. Consciousness exists in a universe of unconscious equations, unexplained by any physical theory, unpredicted by any formalism, present in every branch, yet absent from every equation. The many worlds. Interpretation multiplies what it cannot explain. It postulates an infinity of unobservable worlds to avoid the measurement problem in this one. It does not explain why the Schrödinger equation exists. It does not explain why the Born rule holds. Its derivations are contested. It does not explain the fine-tuning of the constants. It does not explain the initial state. It does not explain consciousness. It does not explain why there is anything to branch. The multiverse does not eliminate the need for a cause. It multiplies it. Science will eventually explain it is not an argument. It is faith. Faith in future discoveries deployed to avoid a present conclusion. Sean Carroll himself, the leading popular defender of many worlds, author of Something Deeply Hidden, concedes that M.W. Boulico does not explain why there is a universe to branch. The concession is revealing. After a century of quantum mechanics, after the most intensive period of theoretical physics in human history, the most fundamental questions remain open. Why does the Schrödinger equation exist? Why Hilbert space? Why these Hamiltonians? Why this initial state? Why consciousness? These are not questions that more experiments will answer. These are questions about the existence of the framework itself. No framework explains its own existence. The evidence points to an intelligent cause, eternal, uncaused, possessing power, knowledge, and will, that brought the universal wave function into existence, configured the Schrödinger equation, set the initial conditions, and established the physical constants within the narrow ranges that permit stars, planets, chemistry, life, and conscious beings to exist and debate the meaning of the equations that describe them. The chain of causes must terminate. An infinite regress of dependent causes would never reach the present. Something uncaused, eternal, and intelligent stands at the foundation, not as a gap filler, not as a placeholder for future science, but as the conclusion the evidence demands when followed honestly. If you found value in this exploration, consider subscribing. It helps these deep dives reach more curious minds. Sleep well tonight in whichever branch of the universal wave function you inhabit. The Schrödinger equation evolves deterministically. The branches proliferate beyond counting. The constants hold their values to 120 decimal places. The fine-tuning permits your existence. The equations describe every particle. They do not explain why any of it is here. Hugh Everett asked his family to throw his ashes in the garbage. His daughter, years later, asked the same, hoping to end up in the correct parallel universe to meet up with Daddy. The many worlds interpretation gives us every possible answer. What it cannot give us is the reason there is a question. The evidence suggests someone knows. Good night.